Hey everyone, today we're going to pull back the curtain on a secret that engineers use to design, well, pretty much everything, from massive power plants all the way down to your smartphone. It's this powerful way of thinking that treats energy not as some super complex physics problem, but as something way more familiar, a bank account.
See, it all starts with a very simple, very fundamental truth. Energy isn't free, not at all. Every single joule of it costs real money to generate, and, it often comes with a pretty big environmental price tag. So for an engineer, wasting energy isn't just inefficient, it's literally throwing away money and hurting the planet. So this is the big question, right? If energy is always trying to escape, how in the world do you track it? How do you control it? And how do you make sure every last bit gets used for something productive? Well, the answer is surprisingly elegant.
Yeah, instead of getting totally bogged down in crazy physics, engineers just reframe the whole thing. They treat energy exactly like money in a bank account. It can't just appear out of nowhere, and it can't just vanish. Every single transaction has to be accounted for. What comes in has to equal what goes out, plus whatever's left over in savings. It's that simple.
And this isn't just some clever idea. It is a fundamental, unbreakable law of the universe. The first law of thermodynamics is basically the golden rule for our energy bank account. It says that energy just changes form. It never, ever truly gets lost.
Okay, so before you can balance the books on any account, you have to know which account you're actually looking at, right? In the world of engineering, this is what we call defining your system.
A system is just the specific thing we're interested in. We literally draw an imaginary box around it. It could be a can of soda, a car engine, or even an entire power plant. And everything outside of that box, we just call that the surroundings. That line between them, that's the boundary.
And this distinction is absolutely critical. A closed system is like a sealed can of soda. No mass gets in or out, but you can still transfer energy, by heating it up or cooling it down. An open system, on the other hand, is more like a jet engine, with fuel and air constantly flowing in and hot exhaust constantly flowing out. How we do our energy accounting changes completely depending on which type of system we're dealing with.
All right, so let's start with the simpler case, the closed system. How do we actually apply that first law to it? Well, engineers have this incredibly powerful tool called the energy balance equation.
Now, whoa, I know. Don't let the symbols freak you out. It's actually way simpler than it looks. All this is saying is that any change in the energy that's stored inside our system, that's the left side of the equation, has to be perfectly balanced by any energy that's transferred in or out. That's the right side. It's just like your bank balance. The change in your savings has to equal all the deposits and withdrawals.
So, how does a system store energy in its account? Well, it's basically in three main ways. You've got internal energy, which is all that microscopic energy of its molecules just buzzing and vibrating around. Then there's kinetic energy, which is from the whole object moving. And finally, you've got potential energy, which is based on its position, like, how high up it is.
And how do you make a deposit or a withdrawal? How does energy get transferred in or out of the system? Turns out there are only two ways. First, there's heat, which we call Q. That's energy that flows simply because of a temperature difference. And the second is work, or W, which is pretty much energy transferred by any other force, like a piston pushing or a shaft turning.
Okay, that closed system equation is nice and neat. But let's be real, most of the interesting stuff in the world, from our own bodies to giant industrial plants, are open systems, where stuff is constantly flowing in and out. And this adds a fascinating little wrinkle to our accounting. So here's the catch. When some mass, like water or air, enters a system, it brings its own energy with it. That makes sense. But there's this hidden energy cost. It takes work just to push that mass into the system against the pressure inside. Think about trying to push a cork into a full bottle of wine. That extra energy is called flow work, and you absolutely have to account for it. So what did engineers do? They invented a brilliant shortcut, a cheat code, really. They created a new property called enthalpy, represented by the letter H. And what enthalpy does is it cleverly bundles a substance's internal energy with all that annoying flow work. And this was a game changer. It suddenly made the impossible calculations for things like steam turbines totally manageable. And this slide just illustrates the power of that shortcut perfectly. Just look at the two equations. For the open system, that U for internal energy just gets swapped out for H for enthalpy. Boom! All that messy flow work is now neatly packaged inside that one single letter. And that lets engineers focus on the useful stuff, the shaft work, the turbine actually spinning, without getting lost in the weeds. It is such an elegant solution.
Okay, so we've got these amazing equations, but they're totally useless without the right numbers. I mean, where do engineers find the exact value for the enthalpy of, say, superheated steam? For that, they turn to a kind of secret weapon, the steam tables.
So just imagine for a second you're designing a power plant, and you absolutely need to know the enthalpy of your steam. You can't just stick a thermometer in it and get a reading for enthalpy. The absolute amount of energy locked inside a substance is incredibly, incredibly hard to measure.
So the solution is to not even try. Instead, engineers all over the world agree on something called a reference state, a standard set of conditions where they just decide to call the energy zero. It's exactly like measuring the height of a mountain from sea level. Nobody cares about the absolute height from the center of the Earth. What matters is the change in height from that one common reference point.
And this is where the steam tables come in. They are these massive books and databases just filled with pre-calculated values for properties like enthalpy, for common stuff like water, at thousands of different temperatures and pressures, and it's all measured relative to that standard reference state. They're like an engineer's encyclopedia. So, we've talked about systems, equations, data tables, the whole shebang. Let's bring this all together now and see how this incredibly precise energy accounting actually engineers a better world for all of us.
And this isn't guesswork, it's a super rigorous procedure. As you can see, engineers follow this clear workflow. They figure out the mass going in and out, they pick the right energy equation, they set a reference state, they look up all the values they need in the tables, and then they solve for whatever they need to know. It's a systematic way to guarantee nothing gets missed.
So why is this precision so important? Well, the big reason is that ever since the 1970s, energy costs have just skyrocketed. We're talking several times over. In today's world, a company that can't account for its energy use with this level of detail, well, it's simply not going to be competitive. It's a matter of economic survival.
And you know what? That precision benefits every single one of us. It leads to more efficient power plants that burn less fuel, which means lower utility bills and less pollution. It means lower manufacturing costs, which makes the stuff we buy more affordable. And it is the absolute foundation for designing sustainable technology. This very principle is at work in pretty much every modern convenience we rely on.
It really leaves you with a final thought. We've seen how engineers tame the wild complexity of energy just by treating it as a simple accounting problem. And it really makes you wonder, what's the next critical resource, like water or carbon, or maybe even data, that we could manage so much more wisely if we just learned to account for it with this same incredible engineering precision? Something to think about.